Well, let's continue on. I think in the early session, we talk about various architecture. I mean, from the mainframe. I mean, going through the desktop interactive computing, and then we talk about cluster system. We talk about world fastest computer. We talk about CPU architectures. We talk about parallel system that has symmetric multiprocessor, asymmetric multiprocessor, and then we'll talk about the next is one of the architecture that I think it touch upon our life, thing that you use it every day, which is distributed computing. The term of distributed computing is quite broad. Okay, it's a system that connected through network and then form some sort of service. Okay, that provide the user um, uh, solving the problem together. The distributed computation is provide distributed computation among several physical processor that connect over the network. Normally, in this type of architecture or system architecture, I think it's formally known as loosely coupled system, which each processor has its own memory, has its own connected device, the I/O. But also each of those systems connect to the other through some sort of communication. It could be wired communication, LAN, WAN, or it could be wireless communication. Okay, so I think we're gonna look into some of these practical kind of application, I mean, of distributed computing, which I think most you guys know about World Wide Web. In fact, World Wide Web is an application of this distributed system architecture. So advantages or the benefit of distributed system is providing resource sharing, uh, meaning that you have collection of resources that can be used in terms of resource sharing. For example, I mean, the term of cloud computing that quite well nowadays. I mean, there are a variety of cloud computing services, such as computing as services, like virtual machine. It could be cloud storage, like the storage as services. Okay. Besides resource sharing, it also improve computational speed. I mean, through load balancing or load sharing, because since you have collection of resources, those resource pools gonna be managed and then distribute the load in the manner of like improve the speed of computation, and also aspect of improve reliability. If in case that one node die, then you have another node kind of replacing. I mean, for example, when you go to www.amazon.com, I mean, behind those amazon.com, there are collection of web server or the either like physical server or virtual servers that provide those services. Some of the node that previously you may access, maybe if there's some sort of a plan to upgrade, or maybe there's some outage that the hard drive dies. If you have single node or not in distributed form, then you're gonna get service interruption. I mean, the computer or the service will not be available. With distributed computing, okay, is an architecture that pull together a collection of resources that will provide you service as single kind of unity kind of fashion. But also, I think besides resource sharing, besides computational speed up, improve reliability, as well as I mean, enable communication. Like email, the whatever the file sharing. I mean, website. They all provide I mean, services that in would kind of enable some sort of communication, as well as various type of services. Um, Basically, the distributed system requires the network infrastructure. The differences between computer network versus distributed computing. Computer network is some sort of a term that equate to a bunch of computer that you network them together, but not necessarily that they may work separately. They may work as single node or single services. But in terms of distributed system, you have not only the hardware, the network, but also some sort of a software system or software service that put on the top, so that it will provide you a more high level type of services. So the network infrastructure could be local area network or wide area network, and also it could be wireless network as well. The in term of client and server, in terms of services, okay, distributed system does not dictate that you have to be client and server only. It could be client and server or peer to peer. The obvious example of distributed application include World Wide Web, which supported by, in fact, World Wide Web supported by the 3 or 4 major protocols such as HTTP, HTML, and the DNS and various other type of service. And then other application that very important nowadays is cloud application or cloud services. That could be infrastructure as services, platform as services, and um, computing as services. I think some of the detail, the cloud computing is quite important, technology that I think you should, if you have chance, you should acquire it. We have a class at Louisiana Tech. I start 5 or 6 years ago. As I told you, I left Louisiana Tech 2 3 years ago and went to Asia and start new graduate college there as the dean. And now I just came back while I was away, so I gave this class to a colleague, Ben, and I think he's teaching that class. So if you have some elective to take, look into cloud, beside AI or machine learning. Okay, cloud, I believe that is CSC 452. Okay, um, besides World Wide Web, cloud, IoT also is, I think, has very strong present nowadays. I mean, people talk about, computing everywhere. People talk about, smart device. People talk about, smart city, all kind of smart thing. Anything is internet enabled that allow connectivity. And normally, only one device, IoT device, would not give any useful kind of application or service. It has to be collection of things. So therefore, I think it's fit into in the form of distributed system. Online stuff, like Facebook or different other online stuff, e-commerce, social network. Okay, those sort of things. They all fit into distributed system architecture. Um, give you a little more kind of idea on internet of thing, or everything is internet. Okay, is essentially internet of thing. It's just beyond the device. A lot of time people think about internet of thing just device. Only device does not work quite well. It has to form an ecosystem or internet ecosystem that you have to have back office, you have to have device which is normally it take the input in terms of sensor command or reading temperature, the CCTV, those sort of thing. Okay, but then all these devices, okay, would have connectivity that would provide um, whatever the data path, so then you can send back to the back office, which normally running on the cloud, and then you can do some analytics, analyze, detect something in a way that it would form some sort of high level services. Application of IoT ecosystem such as smart city, smart highway, smart hospital, and smart factory. I think recently a good friend of mine worked for Verizon. I think he is a managing kind of director on a future technology. I think they deploy a 5G on smart city that they partner with Michigan Department of Transportation, University of Michigan Ann Arbor, and create a M City, which is smart city, which I think they aim toward better usage of 5G IoT in order to form safer, more efficient, and in terms of transportation. They talk about V2X, V2V, meaning vehicle to vehicle, but then using connectivity or 5G in terms of sending and receiving data. Um, I think maybe in maybe a future, if I could introduce or invite my colleagues and giving a little talk on this, okay. I think, or otherwise I'll post his YouTube that I think they showcase the M City, which is smart city in Michigan or Ann Arbor. And smart city, beside that, you have smart hospital, smart highway, smart factory. All and all, I think it's based on all these smart device that you deploy, be able to collect the data, and then you start perform some analytic or analysis in order to make all those data useful in to improve the productivity, to improve the reliability, to improve the performance or security or whatnot. Okay, so I think put on your radar. Okay, your term presentation could be IoT OS or IoT application or IoT ecosystem. Okay, some of these could be potential term paper topic that you can make presentation. But all in all, what I'm trying to emphasize is that all these devices, okay, it must have a layer of system program, which is some sort of a form of operating system, running on those small little devices. Now think about if those devices are wireless or low power. What do you have? What are the unique features of the operating system that you have to be careful or deploy on those devices? I would say, energy efficient, okay, or energy management. I think it's quite useful or helpful in terms of those low power device, okay, that you want to deploy. Some sort of connectivity. I think there are various wireless connectivity that being used or deployed on this device, such as a 6B, uh, whatever narrowband IoT and different others. So I just want to mention all these names in case that you are interested in. You can just Google or find out a little more detail on those. I think this diagram showing this is part of my personal interest in the past 20 plus some years. In fact, before I moved to Louisiana Tech, I was an engineer at AT&T, and at that time, all these smart devices are not very mature. So we have some proprietary device and very immature technology. But I built a new house, my house, which is not a new, I mean, newly built, but 25 or 30 years ago when I was in industry, and deploy some of these idea or concept. So that I can at least turn on, turn off the light, monitor, like those CCTV, and record the video onto the hard drive. And I saw my house that I made profit $50,000, when I moved to Louisiana Tech. But anyhow, various aspect of this smart house or smart living that you have to have a central unit that gather all this information. The central unit could be physical hardware, or it could be in the cloud, whether it's private or public cloud. But then thing that you have to ensure is reliability as well as security. In fact, a few years ago, there's a the whatever the attack that some of the hacker compromise million of uh, whatever the baby monitor webcam, and then take over those, and then use those device as the attack kind of little device, million of them, and start sending inundation of the data or request to DNS server that kill that major DNS server, and then make the whole South America kind of internet down. Um, Now let's shift gear. Look into the paradigm in terms of services on the distributed system. As I mentioned to you, distributed system, the way we use the system is could be in a client and server type of network, where client and server has to have some connectivity, and client could connect to the server and get some sort of service or result. For example, World Wide Web is perfectly fit there. And then you see from this diagram, those clients could represent your notebook or desktop that running on browser, and then you have server could be web server that you hit those server by making HTTP requests. Okay, and then you get some result, whether the website or the web app or whatnot. Okay, another form of distributed system, it doesn't have to be client or server. It could be peer-to-peer or B2B, in a way that the differences between client server and peer-to-peer, client and server, the client always receiving services or result from the client. However, peer-to-peer, each of the client also could be the server, where it can provide the service to another server or another server that could be a client. Example of peer-to-peer is those file sharing that you probably may be familiar, or I'm not. I think, for example, Napster or whatnot. Okay. Um, One of another system that I want to touch upon, and then we're gonna maybe talk about it later on operating system, especially real-time system. Normally, real-time system is oftenly, applied to a mission critical or control device that is dedicated to certain application. For example, the device that controls scientific experiment, the uh, computer control in your car, okay, industry control system, or some display system. So the main objective of this real-time system that you have to guarantee the completion time constraint. We call well-defined fixed time constraint. If you cannot guarantee those time constraint or that time window, you have to deny whatever those service if the user submit request to run any program. Okay, there are a variety of real-time system. Okay, I think we can classify into two type of system. One we call hard real-time, another one we call soft real-time. The hard real-time that you must guarantee, the time completion. Okay, otherwise you have to um, reject those requests. Okay, not execute those things. Okay, so the hard real-time system is critically for the type mission type of critical application. For example, the smart bomb. I mean, when you decide to launch the smart bomb, you must the operating system must guarantee the execution of the application in a way that it will calculate, the trajectory or the path, so that it complete within window of completion. Okay, otherwise it should not allow those missions to launch. Okay, however, the soft real time it relax this time constraint. So in case that you have the new task to execute or compute, and you have existing task that running, if that existing task running it has lower priority. Okay, then the soft real time relax this by um, um, take away the CPU resource from the less fortunate or less priority, and then make sure that the high priority application will be executed in that given fixed time constraint. Okay, that I already talked about this hard real time versus soft real time. So to summary on hard real time, the completion time must guarantee. Okay, it's very critical or vital there. The storage, secondary storage limit are absent. Okay, and the data storage in short-term memory are normally stored on the read-only memory. Okay, if there's some conflict with time sharing, it will not support by the way, the hard real-time system would not support for the general purpose computing or operating system. Since general purpose operating system, you have to allow multi-user multitasking. So therefore, I mean, it's almost impossible that you can ensure the completion time guarantees. Okay, so mostly you have single application running on hard real time. However, the soft real time system you relax the real time so that it limits utilization using normally in industry control or robotic system. Okay, for the hard real time, it usual, for example, I think I already mentioned smart bomb or whatever those car control, computer control car system. Okay, so soft real time is useful in applications such as multimedia virtual reality that require advanced operating system feature in order to preempt some tasks and then guarantee certain execution time for certain important application. A handheld system or smartphone system. Okay, early early on, this handheld system called PDA. If you may heard about the term PDA that stands for Personal Digital Assistant, which I think nowadays it's a smart device or smartphone. Okay, in the old time or early version, I think the main issue of this PDA is limited memory, slow processor, and small display screen. But nowadays, smartphone, for example, I show you Apple A12. It's very capable. It dual core. Some of, like for example, Samsung, you have quad core, have GPU there. So it's much more capable and more powerful. So the issue of limit memory, slow processor, and small display screen would not be an issue. But then still, one issue that remain the same is the power consumption. So therefore, for handheld system or the smart device that does not have power plug-in, power management is quite crucial. Okay. All right. Okay. So I think here is some example of the embedded system, including, I mean, you can see on the left is Tomahawk or Smart Bomb. On in the middle low is computer control car system. On the top is 3D printer, and on the right hand side is the refrigerator, and on the top is robotics. Okay. So I think it also some of them deploy the real-time system, some of them are hard real-time, some of them soft real-time. If I ask you what are these in I mean what are the system that display on this screen, which are hard real-time, which are soft real-time? So I think the answer is the Tomahawk or the Smart Bomb is the hard real-time. Com- uh, Computer control car system is hard real-time. Refrigerator, robotic or 3D printer, those are can be soft real-time. Web-based computing, I think, is another form of distributed system where, I mean, nowadays web is become very ubiquitous. Okay, personal computer are most prevalent device that access web-based system. In terms of web-based computing, you would have a uh, client device or web device, and also you have server that provide web services. Most device become network enabled to allow web access, and nowadays when you have web scale, that means you could anticipate, I mean, very low kind of usage, or suddenly web scale you may be successful. So in that case, the workload is increased tremendously. So in that case, I think you have to engineer and design web-based application that including, using technology such as cloud computing, load balancer, and then have some sort of a a mitigation in case that what if that website or whatever that cloud is not available. You do have any other backup or mitigation. Okay, a lot of web-based support on various operating systems such as Windows, Android, iOS, Linux, or Mac OS. One aspect that quite important nowadays, on the top of operating system called virtual machine or virtualization. If I have time, from this class, I would present you guys one complete chapter on virtualization because virtualization become increasingly important for I think your if you're gonna be in computer industry. I would say most of current modern services, in distributed system, probably would run on either private cloud or public cloud. Okay, and then the cloud computing could not be cloud computing if virtualization technology is not there. Essentially, virtualization, in short, or the result of virtualization would be one of whatever technology that you are familiar with, which is virtual machine. I think most of you guys has your whether window that you can store virtual box that you can run virtual machine, and then that virtual machine you can put operating system on the top. Okay, so essentially virtual machine, it gives you a logical conclusion of the virtual machine or logical machine that provide you a CPU, virtual CPU, virtual storage, and memory. Okay, but then um, the layer in between, okay, is a system software level that allow you to spin up the virtual machine and then manage or tear down virtual machine. Once you have virtual machine, you can deploy operating system running on the top of those virtual machine. And then beside virtual machine, then virtual storage or shared storage also become increasingly important. I think most of you guys probably have used Dropbox, iCloud, or whatever form of network storage or cloud storage. Those are utilized, virtualization kind of technologies. Okay. Um, well, I think we talk about various architecture, both hardware and also system software, conceptual on distributed system virtualization. Now let's just maybe pivot to what, how your computer gets started. Okay. Basically, to start to boot your computer when you turn it on. Okay, there is mechanism in which, okay, it's stored on the EEPROM or the read-only memory. Okay, we call firmware. I mean that piece of software called bootstrap program that would load during the when you power up or boot the system, and then it gonna start initialize, check the insanity, or check the health of your hardware, and then it will point to the boot sector so that it can start load operating system or kernel. Okay, and then after that it gonna start present your window or login so that your computer will be ready to use. Okay, and by the way, the bootstrap program or booting technology could be the term paper that, I mean, if some of you guys are interested in looking into this. Okay, um, now I think let kind of summarize and show you an overall what the word, a typical computer system organization. You have CPU, you have system bus. You saw that line that connect between CPU, this controller, memory, USB controller, and graphic adapter. Okay, if you are using PC system, then you have system bus or Intel bus system that has north bridge and south bridge. Okay, and basically a typical computer system, in terms of to be operational, I think you have to have one or more CPU that connect with various devices, okay, through common bus. Okay, that may be perhaps connect to a bank of memory. Then operating system on the top will help manage all these CPU execution, operation that request running on those devices, and make use of some memory cycle in order to load your application, load your data, and start execute those instructions that part of your program. Now, computer operation or computer system operation, including device operation, CPU execution, device controller, And then from device controller, sometimes CPU may be much faster than memory, so therefore CPU has cache. And then the device controller, some of the device may be much slower than the speed of CPU. So therefore, some of those controller may have some local buffer, so that you're not gonna be bottlenecked by the slowness of those device. Some of these concepts I think we're gonna touch upon again in chapter 8 or 9 when we talk about memory management, when we talk about buffer cache, unified buffer or whatnot. Now, when you execute any instruction, you're gonna move data from and to first from hard drive or your storage to main memory. The memory will be allocated as a process footprint, so that after that, see your CPU can execute those process footprint or instruction that you load in memory. Okay, and in between memory, you may have local buffer, you may have cache, and then somehow when you start execute your program, you may require the access to the I/O device, and the device also completion. Then it's gonna move back and forth from CPU to memory and memory to device. I think we talk about some of these services are privileged service or instruction, and those execution of those privileged instruction on the hardware may have to go through the system called API. Okay, so we're gonna talk about this a little later, but I think in 222 we have mentioned what is the system call and how system call get used. Now, I think we have around 15 minutes left. I think I'm gonna do a quick tour on a various modern operating system and architecture and show you the similarity and differences among them. The first one that I'm gonna show you is Unix or Linux system structure or architecture. This is the high level. I mean, it's not very busy, but also it gives you some sort of an idea and visual kind of mapping to the concept that we're gonna talk later on. Okay, um, if you see the middle layer that encapsulated by kernel, if you see curly bracket on that kernel, so that is the main operating system program or system program that represent operating system features. Okay, and to be able to access those kernel, then you have system call interface to kernel. On the top you have user, and then user could use shell or could use any application command, compiler, interpreter, or whatever the system library, user library, and then to in order to access all those system services such as file system, CPU scheduling, or process management, place replacement, all those device driver, then you have to go through the user have to go to system call. If you are the system developer, in that case you have to know kernel programming in order to control the device, and also an API that from kernel to interface to the hardware. So depend on who you are. If you are just end user, all you need to know is just running some application, or if you write a user application, then you have to know programming language and certain system services. Then you use system call interface to kernel, which is on the third layers. But then if you are the kernel developer or system developer, you may write your own system call or write system services. Then you have to know kernel programming, and then you have to know kernel interface to the hardware type of concept. Okay, where you can access those hardware directly as a system program. Um, Another perspective of Linux or Unix kind of architecture. So from the previous slide, I show you a layer how user interface to application, and then interface to system call, and then eventually talk to the kernel. Now, I mean, we show you the subsystem, architecture that represent in Unix or Linux. Okay, if you look into this diagram, you're gonna see something similar in terms of interface. From on the top, you have user or user program that want to communicate to a kernel to system call. or maybe the user program use the standard libraries that intern using system call that would want to access system service. Okay, and then when you look into system service in specific, okay, you see that there are three major aspects or subsystem there. On the right hand side, probably the most important, called process control subsystem, that underneath it you see the scheduler, the memory management, and inter-process communication. Besides, the core operation of feature that allow you to create, uh, uh, synchronize, and terminate those processes. Okay, and then on the left hand side you have file subsystem. That's not only manage a storage in terms of your data, your file storage, okay, but also manage various device, because the file abstraction or concept is applicable, that we can also use those operations to access not only to regular file but also to any type of device. Okay, so therefore you're gonna see that from file system it has interface to the device driver, that could be character device or block device. Okay, where the block device, since block device normally represent the device that transmit the data in bulk. So therefore, you have buffer cache in between file subsystem. In case that your hardware or your storage is slower, then the buffer cache may make use of some sort of memory or cache system, so that it can read ahead and then store some data in buffer cache in the big bulk, so that it will not slow down your total application. And then if you're seeing underneath device driver, then it will interface to hardware control, okay, which is still within the kernel level, but underneath it you see the hardware level, that you have the interface between kernel and hardware level. So I think in the sense that if you understand the previous diagram, okay, that's showing various type of operation, okay, versus in this diagram that's showing the subsystem, important subsystems such as process management, memory management, file system, device management. Okay, it works hand in hand quite well. Okay, so I think in the sense that this is a Linux kernel or Linux operating system architecture. Um, Throughout this class, I cannot show you this architecture more often, and then start showing you or deep dive into subsystem, particularly, we'll start with process management. Then you look into the Mac OS. Okay, now the Mac OS, and if you see that underneath it, you have hardware, and then on the top you have kernel, which there is a mixture between BSD and Mark. Okay, and by the way, BSD is Berkeley distribution, which is a Unix type of architecture. So essentially Mac OS, okay, is adopt the concept or architecture of Unix or Linux. The Mark is a microkernel, which is the concept that we're going to talk about later on. Essentially it's just the way you manage certain type of service, that you would take some service outside the kernel, so then you can optimize not going through the overhead when you make some system call. Okay, and then on the top of the kernel you have various service that's sitting on the top, including a graphic user interface like the Carbon Core, okay, the Coco, the QuickTime API, and various either GUI or non-GUI type of interface. Okay, and then in between, the connection between top layer API and the lower level, it also deploy using Java type of services. Okay, and then on the top you have graphic user interface called Aqua. Okay, but essentially, you can see, the subsystem is broken down into its own kind of functionality. Okay, what it's supposed to do well. um by the way, I don't expect you to remember all this. I think, as I told you, memorization, I think it's quite dangerous. Understanding, follow up the concept, and then see what work and how they plug in together and work together. I think that's the concept is very important. Next one is Android, and if obviously, if you look at the bottom, I think it's all with the hardware interface. So you have Linux kernel as a foundation of the Android. And then you know that Android, basically, the first development of Android is toward uh, the smartphone system. So therefore, on the top, you see that phone services, and then in between, you see various services that add on into or enhance from the basic foundation of Linux kernel. So don't worry, don't have to remember the whole thing. I want you to see the similarity and the differences. I mean, among various operating systems. Next one is iOS, okay, which is similar to Mac OS, but I think here I'm just giving you a shorter version. Remember, when we talk about Mac OS, on the top we have Cocoa, okay, whatever service, which is more in terms of user interface, and then you have layer of the hardware, the firmware, the processor, the phone OS, the object type C runtime, which is to handling certain system services, okay, and then the framework API and the application on the top. Next one is Windows, okay, but I think particularly the one I show you, I think it's Windows, I believe Windows 7 or Windows 10, which the code name is Longhorn. But basically, even Windows 10 right now, architecture wise, not much different uh, from whatever this Longhorn here. As you see that, you see the basic operating system services, which is the kernel sitting on the bottom left, okay, where you see that memory management, process management, all main core operating system services sitting there. And then beside that, the window architecture, okay, decide to separate, I mean, different services. For example, presentation, which is user interface, the data, which is mean toward, like some file interface, okay, have separate modules, communication and networking, okay. So I think don't worry about, I don't expect you to remember all this, but then I just want to see, I think the core thing, the key thing is they all have common uh, feature or core operating system feature, okay, that's sitting on the bottom. The Chrome OS is just a lightweight Linux kernel which is deployed on a thin server or a system that rely more on web application. So basically, I think it runs Linux, a stripped down Linux kernel version, and then on the top it has some sort of a graphic library that based on X window. When you see X plus graphic library, is X window, which is not new. X window has been introduced probably almost 20 plus some years, but still being used nowadays. Most Linux operating system, when you start running Ubuntu or whatnot, KDE, that's all based on X window. And then on the top you have Chromium service, and then you have web app, website, and extension there. Okay, and Fog OS is similar to what was this Chrome OS, but again you see that there's a Linux kernel underneath it. There, so I'm not gonna go to all details, but I think you just for the kick you can review this. And by the way, these various operating system, okay, it could be idea of your term paper again, virtualization. I think when we have time, we're gonna go into more detail on virtualization. But one of the most virtualization um, company or application called VMware. So in fact, VirtualBox is one of the system that you use, which is open source or the free version. And then you have VMware, you have Zen, you have different others, virtualization tools. Um, and then I think this picture just show, I mean, different hardware can be virtualized as virtual machine, and then you can install different operating system on the top of those virtual machine, and they don't have to be the same operating system. One box or one server. I mean, you could have maybe a few virtual machine, and then each virtual machine can run, one virtual machine can run Windows, another virtual machine can run Linux, another virtual machine can run, the third operating system. um, just want to mention to you, I mean, VMware, that's the industry leading company that market whatever this virtual machine or virtualization tools that allow you to create virtual network, virtual machine, and also now integrate with OpenStack that allow you to create a private cloud or public cloud. So in the sense that, I mean, besides you create virtual machine, it also has ability to manage multiple virtual machines together and form a cluster or a collection of resources, so that, I mean, it can provide the service. Okay, the whatever the window, the pop-up window underneath that one is a dashboard that you can use to configure network or to deploy whatever the node, the virtual machine. Okay, and then form a cluster of public cloud. Okay, or private cloud. I think this is just a picture represent, I mean, multiple cluster. In fact, all those cluster doesn't have to be a hardware, but then is in the form of virtual machine. So why don't we do this? Let's stop at this point. I think we gone all over, a little more than, our normal meeting time, an hour 50 minutes. Okay. Again, I apologize for little hiccup this morning. I have some audio issue. I suspect that because I used different like Bluetooth device and then connect to it's mess up my connectivity. So therefore, I think I have some issue, but I'll make sure that I will resolve this issue next time. And I hope to do the live broadcasting, because I think I like more interaction. I want you to kind of follow me, and then you have question, you can type on the live chat or the feedback, so then I will try to read and answer you live there. So I want to make sure that you have good experience, good learning experience, and then anything that you need, okay, let me know. You can either Skype me or text me or call me, but please text me before you call me. Okay, my Skype is NAIBOX. Okay, it's my screen name, you just add there, or my cell number, but don't post my cell number to the public. Okay, it's 318-243-6597. Okay. All right, so long, and we'll talk next time. Okay, I hope I think we go smooth next time. Have a good day. Bye bye.